Hi folks, I hope you all be well. My name is vicentefachina and I work in the oil and gas industry. This presentation stems from my interest on the entropy concept beyond thermodynamics since the 80s in the past century, when I was an engineering college student. I got interested on how to apply this powerful concept as a general framework in realms other than thermodynamics. This is the summary in two parts. One, in the theory of entropy metric, and an appendix for an application in economics. This is about energy and how to apply general equilibria in conservative systems to enable calculations by equating supplies and demands. By making the product between a coefficient array and a demand vector U, which is the inner uses and rejections in each demand element, that product yields a supply vector X. On the other hand, the supply vector stems from the environment's availability and environment. The coefficient array itself stems from making the networks among all elements as partitions, the coefficient themselves of the elements UK themselves. This is a bottom-up approach for entropy that hinges upon conservative systems for defining entropy metric, the fundamental G array, which operates on the system demand elements, the U vector, to yield the entropies related to each demand element, the S vector. Thus, the more connections, the less entropy. The summation of all such entropies yields the system's entropy, the S-scalar. Note, the G array is a metric, but a tensor. Entropy depends on the finite references, measuring units, local time. Thus, the entropy metric is not a tensor. This is a top-down approach for entropy by applying definition of entropy as the negative array product between the main elements, the U vector, and the respective variations of their networks as to the other elements. By separating entropy into two parts, the entropy brought about by the main elements themselves, and the one by their networks as to the other elements, one concludes the entropy of any system together with respective environment increases both in an isolated system and in an open one. The 3D plot stems from a linear entropy model. For instance, in economy, more entropy means either inflation or credit debt expansions. The more inflation, the less networking. Or the more credit debt expansion, the larger the demand elements, both with increased entropy. Note, the SUW values are relative to defined references, the values of which are set to null. Efficiency is a classic definition, the output per input ratio. The larger the better. Nevertheless, if applied on both extremes, the very beginning and the very end of a demand element in a conservative system, one gets. At the very beginning, the inception of the demand element, there is no network out of a positive inlet for the very inception to happen. Thus, efficiency is null. At the very end, both a demand element and its net inputs are no more. Then efficiency as to net inputs, x, becomes 1. Here there happens a 0 to 0 ratio by the definition of efficiency, so the L'Hopital rule does apply. In addition, if one calculates efficiency as to the gross inputs zeta, then it is null because environment is never null. In order to get both yields, the null efficiency at the very beginning and the unity efficiency at the very end, I devise a dynamic definition of efficiency from null normalized time towards unity normalized time. The plot shows both efficiencies, the net efficiency and the gross efficiency. Here I develop entropy as to normalized time, tau. By plugging the previously defined lifetime efficiency into the entropy model that uses the log function, I devise an entropy function with the following features. 1. Entropy is null at null time. True, entropy might eventually be both asymptotically positive infinite and negative infinite at unity time. Besides, entropy actually oscillates, with lower entropy activities bringing about higher entropy ones, and all within an underlying increasing overall entropy of system plus environment towards some maximum value, ever. Here, I revisit the classical definition of temperature from thermodynamics, which is the partial derivative of energy as to entropy by plainly making the unit energy to entropy ratio. The reason of which is to avoid having a continuous function. By deriving the relative size of a demand element U minor as to normalized time tau yields a differential function as to temperature and entropy. Now, by defining a flat steady-state system as to having null derivative of the relative size of the demand element, and by plugging into this differential equation the entropy function developed in the prior slide, one gets a temperature function for which the system remains flat or steady. In a steady-state system, the relative sizes of demand elements, U minor, the U to X ratios, do not get any smaller or larger. Such a function might serve as baseline for comparisons with actual temperature values in conservative systems. Here, I devise an efficiency upper threshold function, the W to X ratio between total work, which is network plus the element's inner workings, and inlet X, which has to be smaller than the lifetime efficiency which was developed in the prior slide. Here I develop three equalities up which every thriving system should follow. The summation of the coefficients in the coefficient array should target threshold values, the red line in the plot, for minimum entropy as to normalized time. The plot shows the existing region of a system within common normalized time. From high element interconnections towards none along a finite time. Here, I ask myself, what if time is not an independent parameter, yet actually depending on entropy? Tau as of S, the hyperbolic tangent as inverse function does a good job. Note the derivative d tau over ds at 0 tau is 1, and at 1 tau it asymptotically converges to null which means elapsed time grows slowly towards the very end, and it picks up fast at the beginning of time. In addition, I add light blue features on the plot developed in the previous slide to illustrate the highest entropy in the end might eventually turn into the smallest one in another environment and time. Thus, a new start might follow on. And that's all, folks. Bottom line, if there happens to be no interconnections, entropy is the highest one. If one substitutes information for interconnections, then one defines entropy as missing information. Entropy is null for no missing information, and entropy is maximum for no information. For instance, a project role is to decrease entropy by proper delivering planned scope towards creating either products or processes which follow their purposes with increasing entropy, then new projects might come along eventually to reduce entropy, and so on in cycles. Now, I feel the need to encapsulate all such equations into a poem on entropy and time. Dance of time. Time is born from bonds. It flows slow if chaos grows, few or no bonds. Bonds are born, torn, worn, yet time weaves its fate by strong, many bonds. As bonds fade away, the end draws near. Last bonds yell loud and clear. O time no more, yet not timeless. If bonds had risen elsewhere before the end, new time is born from what had been. This appendix illustrates the application of the entropy metric on economics. This is a Sankey diagram for the US energy conversions in 2021. This is a plot of the unit size of the fossil fuel sector spanning 4 decades as of 2021. The red dot is the calculated unit size of the fossil fuel sector from the 2021 Sankey diagram, and the two yellow dots are forecasts for 2041 and 2061. The upper red dotted line represents a low efficiency path. The lower red dotted line represents a high efficiency path. And the black dotted line represents an average efficiency path. This is an energy map, the coefficient array for the USA by 2041, with the premise of the same total net energy input as of 2021, which was about 97 exajoules. One tweaks the coefficients in the off-diagonal array for yielding a target about 35% unit size of the fossil fuel sector by 2041. The tweaking was halted by 33%, and the simulation runs ended right there. This is the energy map from the prior slide in graphical form. The red shapes represent the primary energy supplies. So, the contributions of renewables and nuclear energy carriers are simulated to rise from 21% in 2021 to 31% in 2041 in the USA. The premise of isentropic economic processes brings about 60% overall energy efficiency, the same as of 2021. Thank you very much for your attention.